So welcome to Lean Together 2025. This is the first talk at the conference, and it's by Oliver Nash, who's my former postdoc and now working at Google DeepMind, and he's going to tell us about root systems and root data in Mathlib.
Thanks, Kevin, and Gyro and Ricardo for organizing it and letting me speak. Delighted to be here. It's half an hour back in my academic world instead of in DeepMind, which is nice. Okay, so before I launch into what I want to say about root systems and root data, I should point out that first of all, I'm a minority contributor to this part of the library. Scott Carnahan has actually developed most of the theory. And second of all, I didn't even do the first formalization of root systems in Lean. This done by who wrote a finalized about root systems, so he did the initial work. So why am I here at all? Well, what I did do was a year and a bit ago was I added the definition of root systems and root data to Mathlib, and as you probably know, definitions are often a little bit more work than lemmas when it comes to writing the code for Mathlib, and I thought this was just a particularly good example of the idiom that like good definitions can be hard work. So yeah, I want to just give this as an example of like how that can go sometimes. And I learned myself, little bits of facts about this that I otherwise wouldn't have. Okay, so I'm not presuming everybody knows what root systems are. It's not going to be a highly technical talk where I'm asking you to follow detailed arguments. But I would like to give you a sense of what root systems are if you haven't seen them before. So I have an opening question, which I think should make sense to everybody, which is, supposing I have a finite dimensional vector space, and I want to understand some endomorphism of that, how do we do it? And we've got nice coefficients for an algebraically closed field. Well, we all know the answer, I think. Use eigenvalues. You can decompose the space as a direct sum of generalized eigenspaces, and depending on what you mean by understand, that goes a long way to helping understand this endomorphism rho. And the thing that I want to take away is that these are the eigenvalues, and their type is a finite subset of scalars, your field. So you ask this question, I'd like to understand an endomorphism, and the type of the answer is a finite subset of scalars. Okay, so we're not at root systems yet, but we're on our way. Then you have a follow-up, or I have a follow-up question, which is, let's ask about families of endomorphisms. So, often it's useful to look at families of objects in mathematics, and so we do that here. And you say, okay, now instead of just understanding a single endomorphism, I'd like to understand a family of endomorphisms. So that's the question. What's the answer? Again, it's eigenvalues, except this time it's simultaneous eigenvalues. So again, we can decompose the ambient space, this vector space V, as a direct sum of, this is simultaneous generalized eigenspaces. So each endomorphism rho X is varying through L, has an eigenvalue alpha X, and you sum over these alpha and you get a decomposition. Okay, you need the rho X need to have some compatibility condition, but if they commute, for example, that's sufficient, but there are weaker conditions they can satisfy that are also sufficient. So that's fine. And as I say, instead of scalars, we have replaced operators with family of operators, and eigenvalues get replaced with families of eigenvalues. So this time the type of the answer is a finite subset of functions from your parameterizing your indexing set into the scalars. Okay, so then the next question you can say is, all right, well, I've just generalized, now I'll specialize a little bit. So what if, instead of just any old indexing set L, what if it's a finite dimensional vector space? And once I have that structure on L, I can now say, and what if my family of endomorphisms is linear? So L has now got a linear structure, and so I can ask how to understand this. Well, the answer is going to be the same. I know, I'm going to get a decomposition of simultaneous eigenspaces as long as I've got the compatibility condition between the endomorphisms. So what extra thing happens? Well, what happens is that these families of simultaneous eigenvalues, they become not just random functions of any shape, they become linear functions. So again, some mild conditions need to be satisfied, which, for example, are satisfied by commuting operators. So now what we get is, we started out with the type of the answer was a collection of eigenvalues. It was a finite collection of scalars. Then we got a finite collection of functions. Now we've got a finite collection of linear functions, which of course is just the dual. So we've got a finite subset of a vector space. So that's the type of the answer now. And it's just one more step now when you get to root systems. You say, okay, I'll specialize even further. I'll give L some extra structure. And instead of L being a vector space, I'll suppose that L is a Lie algebra. So every year for the last few years, I spend a few months working on Lie algebra theory for Mathlib. So this is a familiar question for me to ask, but Lie algebras are central objects, and this question has been an important one in mathematics for 100 years or so. So now you're asking about, I have a representation of Lie algebra morphisms parsed by Lie algebra. Some subtleties arise from the point of view of today. They don't really matter, but technically you need to restrict to nilpont and subalgebra, and you need this to be the right type of Lie algebra. But I'm just putting that in for honesty's sake. They're not really so relevant. But then the question is like, okay, fine. So there's a cost to bring in the Lie algebra, rather than just any linear family. I need to worry about how to get my simultaneous eigenspaces respecting each other. But what's the benefit? Well, the benefit is there's a short calculation you can do. And I don't really want to, the reason I have this calculation here is just to illustrate how short it is. I mean, the actual details of it, I don't think we need to worry about them right now. But the point is, this is a 3-line calculation. And the result of it is telling us something immediately about this set of simultaneous eigenvalues that happens and is special to this case when you have a Lie algebra. What it says, the result of this calculation in English down here is that if alpha and beta are simultaneous eigenvectors, so they're elements of this dual space, they're vectors, and either alpha plus beta is also a simultaneous eigenvector, or this property here vanishes, these two elements commute. And so this is like, now you've got the additive combinatorics of this set of vectors, these simultaneous eigenvalues, is connected with the algebra of the object that you started with. This is a statement of two elements commuting. And so you have yet more structure on this finite set of vectors because of the Lie algebra structure. And so the moral is that this collection phi of simultaneous eigenvectors, it's now a finite subset of this dual space, of this vector space, satisfying some combinatorial restrictions. And you need to pull on this thread here a little bit to figure out exactly what those combinatorial restrictions are, and to get statements that are wholly intrinsic to this set phi rather than still being connected with the algebraic structure you started with. But that's exactly what Killing and Cartan did at the end of the 19th century. And they worked out that these collections of vectors that you get are finite subsets of a vector space satisfying some combinatorial restrictions. And these now are named root systems. Okay, so that's the motivation, that's the background. So then, what you'd say, well, what are these combinatorial restrictions? These are the axioms of a root system, so I'll give them to you. It's a finite subset of this dual space. Actually, there's a natural inner product that comes from the algebraic origins. And then this inner product I denote with these angle brackets, and you have 3 axioms. So the vectors must span, they must not be null with respect to this inner product. And then because you have this symmetric bilinear form, you have a concept of orthogonality, and so you can talk about reflections. And so given a root, or given a vector alpha, you can talk about the reflection in the hyperplane perpendicular to that. And this is the key combinatorial condition. Reflection of this set phi in the hyperplane perpendicular to one of the roots. It's not just some random other collection of points, it's actually the original set of points that you started with. So these are the axioms of the root system that Killing and Cartan worked out. And this is like, if you want to understand classes of Lie algebras, you're going to need to understand this. And so, then the question is, all right, fine, I need this, I want to add this to Mathlib, so maybe I should just formalize that definition. Oh, and yeah, I also just have a picture, just to make this a little bit abstract. I've taken this picture from Wikipedia, but this is an example, if you haven't seen one before, of a particularly nice rank 2 root system. It's sitting in a 2-dimensional vector space, so I can actually draw it. And this is not schematic, this is like the literal truth. There are 12 points here, and these are the 12 elements of this root system. And you can convince yourself, if you reflect in the line perpendicular to any one of these arrows, that set goes back to itself. And if you spend even more time, you can probably begin to convince yourself that that's quite a special property and not so easy to satisfy in general. Okay, so that's root systems. We have the definition, we have some intuition for what they look like, we have examples of them. we want to have a definition in Mathlib so that we these things. Let's have a go. Now that definition that I just gave, which is probably the most popular definition of root systems if you look on Wikipedia or various books, this is what you'd write. And this is a pretty good definition. So I've got a finite dimensional vector space over a field of characteristic 0. I've got this finite subset of vectors. So M here is like H star. We've got this bilinear form. It's symmetric. It's non-degenerate. The roots span. None of them are null. And then this condition down here is a little bit of a mouthful, but this is saying the reflection associated to a root alpha, it sends phi to phi. And so, that's valid lean that I wrote when I was making these slides. And then the question is, should you use this definition? You certainly could. You could develop a good theory on the basis of it. But there are some aspects of it that are worth pausing for thought about. One is, it's not obvious, actually. I mean, it's not super deep, but it's not obvious. The bilinear form is actually uniquely determined. So that's one thing. And, including uniquely determined data is a reasonable thing to do, but it's something you should think about. Like, we include the identity as data in our definition of a group in Mathlib, along with a lot of other uniquely determined data. But it was a deliberate decision. And so you should ask yourself, would you like to include the bilinear form? So that's one question. A more serious question is, I also mentioned root data. So, we'll get to root data in a minute. Root data are, roughly speaking, root systems where the coefficients are the integers. So, and, often you see, in fact, I've only ever seen a treatment of root systems and a treatment of root data. I've never seen a unified treatment of the two together. Nobody's actually bothered to just do it. But in Mathlib, we hate to repeat ourselves. So I would like a unified treatment of the two. And so if this is going to be a definition of root systems, I'd better try and make it something that can also, cover root data. And as it stands, it doesn't, because in here, this is an expression that occurs in the axioms. There's a division, and that division is fine because my coefficients are a field here. But if I want somehow this definition to work or be made to work for root data, where my coefficients are the integers, I'm going to have a problem. So the answer, should I use this definition, is probably not. So, okay, what can you do? Well, you can look for other definitions of root systems. It's a sort of standard exercise of what you do when you're developing Mathlib is like, make sure you look at all of the definitions that are in the literature and choose the one that's the most appropriate. So there's a prolific French mathematician, very long-lived, called Bourbaki, and he has a definition of root systems. So what's Bourbaki's definition? So it's different. I mean, it's mathematically equivalent, but it's definitionally different. So this time, again, we have a vector space. We have a finite subset. It must span. So far, this is the same. The bilinear form has been dropped, but instead, there's this condition that, for every root, you can find a linear form. The kernel of this linear form is going to be hyperplane, and that's like morally the hyperplane in which you're going to do the reflection. So if you have this linear form alpha check, then you can talk about the reflection in that, and you require to take the value 2 on the root. This corresponds to the fact that if you want to reflect alpha, alpha should go to minus alpha, and so you're subtracting 2 times alpha. So that's where this 2 is coming from. And then I can, just from having alpha and alpha check, I can write down the reflection. So this is the elite linear map which fixes the kernel of alpha check and which sends alpha to minus alpha. So I call that a reflection, even though I've dropped the bilinear form. And then the axiom is the familiar one that we had a moment ago, which is the roots are preserved. So this definition is better. This has the advantage that there's no division in it. And here it is in lean. This is pretty good. This is actually the definition that I gave to DeepPro when he was working with it, and it was useful to see it explored by him. Okay, so I'm going to repeat it again. So okay, so this is second attempt at having a definition of root systems. And so the question is like, should I use this? It's mathematically equivalent to the first. So far this is not going to give us any different theory. But different questions come up. So these co-roots, what the alpha check are called, these are actually uniquely determined. Maybe they should be part of the data. At the moment, we're just asserting F is alpha check in this context. We're just asserting that they exist, but maybe we should actually include them as part of the data since they're uniquely determined. And then the next question that I'd ask myself maybe is, the reason I didn't like the first definition was primarily I want to be able to cover root data. So, is this sufficient? Now there's no division, so I don't have like a type error when I'm trying to divide, 5 by 7 in the integers, which, is not going to give me a useful answer. But, have I mathematically got the right concept? So in other words, if I make this change, Lean will now accept this change. I can naively weaken my assumptions and Lean will agree that I've defined something. But like, am I defining the right thing? So the answer actually is no, not yet. So, how do you answer that? Well, you say, okay, let's try to understand the mathematics a little bit more. So I've given the precise statement here, but the important property is that I'm leaning on, by not including the co-roots, which so far in this definition I haven't, I'm leaning on the fact that the co-roots are unique. But there are some assumptions to get that. So one is that I have characteristic 0, and the other is that the roots span the ambient vector space. So you say, okay, well, I better, if I'm going to try and continue with this definition, I'm going to try and continue developing the theory, because there's an existential here, rather than actually including the co-roots as part of the data, I better keep an eye on these two conditions. And if they ever get dropped, I better rethink my definition. Okay, I'm also going in the direction of root data. So, okay, what are root data? Well, where they arise when you have tried to do this classification of groups rather than the algebras. There's some conventional choices that are made that don't matter too much for us. But the important thing is we're now working over the integers. And so instead of M being a vector space, M is now just some finitely generated free abelian group. There's also N. You can just think of N as N star. Okay, and so let's have a look. Let's see, are we ready to also have our definition cover the definition of root data? Well, the answer is no. Right? So root data, it looks like a different definition, but the thing I want to call out is there's no longer a spanning condition. And so this is the reason that, the definition of root data that Michael de Major came up with, he includes the co-roots as part of the data. So, answering our questions earlier, which were like, should the co-roots be part of the data? The answer is yes, because co-root uniqueness only follows from the spanning condition. And indeed, this is consistent with the correct choice that was made historically for root data, which is that the co-roots are included. So, okay, you're like, all right, fine. So if I want to cover root data, I still need to do some work. So I'll have a third definition. So this is now, and actually when I was developing this theory, this is not exactly the path that I took, but this was roughly what happened to me. So now you say, okay, I'm going to try and have a definition of root systems, but it's also going to cover root data. So I call this a root pairing, and then it's going to be able to specialize to root systems, or it's going to be able to specialize to root data. And so I have the roots. That's this finite set of vectors that we had all the way back at the beginning. And I've just realized I definitely need to include the co-roots, either because I just checked SGA3, or because I looked carefully at the, co-root uniqueness lemma conditions, and I noted that spanning condition was important, and that in general I don't have the spanning condition. You need to have a bijection between roots and co-roots, and then this thing here that looks like a big mouthful. This is just saying, if you have this data, you can build reflections, and the reflections preserve the roots, and the reflections preserve the co-roots. So that's the usual condition, but now for both roots and co-roots. So that's fine. And if you happen to have a root system, you have to add in a spanning condition. So this is now mathematically correct. And furthermore, I'm using a commutative ring now, and that's no longer like a naive weakening that does something silly. This will indeed give you a useful mathematical object, and in particular, give you a root datum. So you could say, should you use this definition? It sounds pretty good because you've got root systems correctly covered, root data correctly covered, and also it's definitionally fairly nice. But the answer is still no. You still shouldn't use this definition. This time, the problem is that it's it's type theoretically awkward. So I worked briefly with this definition for a day or two, and I quickly encountered what we call dependent type theory hell. So this is when you have data whose type depends on other data, and you almost always want to avoid this. So here I have two pieces of data, phi and psi, and then I have this additional piece of data, E. E itself is data, but its type depends on this. And so this is what dependent type theory enables you to do, but it's almost always a massive pain in the neck. And indeed, when I tried to prove theorems about this definition, I quickly decided I hated it. So then I was like, well, this is a bit disappointing because, I finally got something that's mathematically what I want. And now the type theory is making my life, not worth living. So what do you do? So, one thing you could do is, the problem here is E. It's this bijection. I could, for example, decide to follow this junk value pattern that we sometimes do in Mathlib. So I could say, well, E could be defined on all of M, and it could take values in all of N, but I'll only care about its values on psi. And that would work. And actually, that would be okay. But I still decided I didn't like that, partly because the junk value pattern is useful, but as a last resort. And I had other resorts. And secondly, because I really wanted to make this definition as symmetric between roots and co-roots as possible. And there's an asymmetry. There's just one asymmetry in this definition still, which is that E has a concept of a forward direction. It goes from phi to psi. Now, the inverse exists, and that's part of the data. But still, there is a concept of the forward direction here. And that's an asymmetry. So I thought about that a bit more, and I said, okay, here's definition 4. And I was very pleased I mean, it's obvious, but I was very pleased when I started working with this, because then I found I could prove everything, and everything was really nice. And it's quite a similar definition. All I've done is I've introduced another carrier type, which I called iota for indexing. And now the roots, instead of being a subset, they're just, an injection from this finite indexing set. The co-roots, totally symmetric. So I've split this bijection by just inserting a type in the middle. And so the bijection is now just implicit in the fact that both the roots and the co-roots are indexed by the same set. And then the other axioms are more or less the same. So this is now type theoretically nice, and it specializes to roots, to root data and to root systems, and I can prove useful things about it. And so that I thought was pretty good. And I actually added this definition together with some basic API to Mathlib, and I thought that was good. The only thing is that then Scott Carnahan showed up. Now, Scott's an expert in infinite root systems. And he pointed out, this is wrong for an infinite root system. So, and then later still, actually, after the problem got fixed, I thought about this a little bit more. And I realized that I might one day want to drop this characteristic 0 assumption. And so then I was like, oh yeah, and it'll actually also be wrong for positive characteristic. And then I thought, wait a minute, is there even a theory of positive characteristic root systems? And it's a bit of an exotic thing, but it is real. Like, there is a classification of certain well-behaved types of modular Lie algebras, and they have such root systems. So I asked on Math Overflow, like, no one has developed this theory. It's implicit in the classification of Lie algebras, but nobody has abstracted it out. So again, that's the sort of thing, like, when you get into this quite edgy stuff, it's actually not hard to just get outside the bounds of the literature. I mean, this stuff is, in people's heads, but it's not written down anymore. Okay, so definition 4, which even got added to Mathlib, and is a good definition, is not a good definition in all the cases that you'd want. And in particular, the important case, people really do care about infinite root systems, of the deep and beautiful theory of, Kac-Moody algebras, infinite dimensional Lie algebras with infinite root systems. So definition 4 also had to go in the bin. But the question is, what's wrong, right? Scott has explained it, of course, but what's wrong with definition 4? Well, there is, I didn't have a name for this. Maybe there is a name, but I called this consistency of the Weil group permutation action. So if you have a root datum, so let's just, if it's finite, you can take the jth root, you can reflect it using the ith root, and you get another root. You can do the same operations. You can take the jth co-root, reflect it by the ith co-root, you get another co-root. The point is this k is the same as that k. So that's a lemma that's proved like early on in the theory of anybody who's doing root data or root systems. But it needs finiteness, and it also needs characteristic 0. So, nobody ever really cares about this stuff normally, because they're always in that case. But when you're trying to unify everything and have just one definition that everyone can use, suddenly you care about all these. So, so this is a problem. Solution is you make this shouldn't be a lemma. This should be a definition. This should be definitionally true. And the dilemma is that if you have these properties, well, then actually that can be derived from less data. But in general, the object you're defining, it should include this. Okay, so Scott, he didn't just point out the problem, he also provided a fix, which is very nice of him. And what he's done is he said, right, if when you reflect any root, you get another root, and that permutation, that permutes the roots. That's the same permutation as the co-roots. So really, that's the fundamental data. Is you have a family of permutations. I mean, this is like, we know this is the Weil group permutation representation. So he said that should be the fundamental object that's part of the data. And then these are the two axioms which previously said that the reflection preserves the roots. Now it says the reflection permutes the roots according to the data of this permutation. And then critically, that same permutation is the one that appears in the co-roots. And so now, we have this, should we use, and then the question is like, we're on definition 5 now. And since about 3, I thought I had it right. And even 1 and 2 are pretty good. Should we use this definition? So the answer is, I think so. This is what's in Mathlib today. And we've developed a respectable body of theory about this. So I think this is pretty good. It doesn't assume characteristic 0. It doesn't assume finite. It simultaneously specializes to, any situation that you like. I feel like this may be the first time someone's actually really figured out the essence of this mathematical structure. It's quite satisfying. So yeah, so that's it. And you think, okay, we're done, right? The job, of course, is develop the theory, but for me, the job is just to get the definition right. And then somebody hopefully will take it from there. But no, you're still not finished. So this is more just, now in the kind of philosophy of library building, what are your responsibilities? You can't just dump in a definition. Nobody will be able to use it. So you must build API around it. And the really basic important API for the root system is, I talked about uniqueness properties. Actually, I didn't really mention this, but the bijection between roots and co-roots, again, it's a fact that's established early on, and it should be developed as part of the API. That's a natural extensionality lemma. Co-roots are unique a lot of the time, right? When the roots span and you're in a characteristic 0 and things are finite, and yeah, that's sufficient, then the co-roots are unique. So you must write an extensionality lemma for that. Otherwise, people who are working with your theory will say, but these two root systems are the same. Why do I have to prove the co-roots are the same as well? So you must have a lemma there for such situations. And you also must write custom constructors. So we've made root systems extremely definitionally strong, but that means they're very hard to build. But a lot of the time, people will be in very fortuitous situations. They'll have finite collection of roots. They'll have characteristic 0. So then they'll have spanning roots. They'll actually have a root system. So a lot of the properties that are demanded by definition actually just hold automatically. You only need to give a subset. So you must write custom constructors. And yeah, these are the various conditions. So and then you're finished. You get your 5th definition in place. You write your extensionality lemmas. You write your custom constructors. Now you've defined root systems and root data in Mathlib. And then so I wanted to give this kind of lightning talk of that experience because I thought it was fun. And the lessons that I decided to take away are good definitions are hard work. You should always look ahead. Like, I don't have plans to use root data in the near future. I hope that, we will one day, add the classification of reductive algebraic groups to Mathlib, and then we'll need them. But I wanted, things to be done right so that they're ready when that day comes. Avoid naive weakening of axioms. Like my second definition had an advantage over the first in that it now made sense for commutative ring coefficients, but it wasn't what I wanted it to be. So it would have been wrong to just naively weaken the axioms. Take definitional control. So you want to avoid this dependent type theory hell. Usually you do that by introducing an auxiliary new type. So take definitional control. You must write the API for your end users. And yeah, it's easy to encounter. I mean, I guess I call these open questions, but questions that you ask them on Math Overflow and people are like, yeah, I'm not sure. So yeah, so it's like, that was my experience developing that theory. It was fun. I learned a bit, and it was very, very encouraging that, a few months later, somebody started using that definition, and now there's this, very nice body of results that Scott has developed, in Mathlib. So yeah, I think I'm done.